Question 18.3 asks us, what is the strongest type of intermolecular force in the following compounds? Much like 18.1, our three options are dipole-dipole interactions, London dispersion forces, and hydrogen bonding. For a quick review of how we decide between which intermolecular force is acting primarily on our compound, the video for 18.1, we go a little bit more in detail here, but essentially we can tell that if the molecule is nonpolar, then the primary force acting upon it is London dispersion forces. If the molecule is polar, but there isn't an H bonded to an F, an O, or an N, then we just have dipole-dipole interactions. And if there is an HFON bond, then we have hydrogen bonding. Starting with CH3NH2. So the first thing we notice is that carbon is bound to nitrogen. Nitrogen is more electronegative than carbon, so we already have some sort of pulling of electron density away from carbon toward the nitrogen. However, we also see that there's a nitrogen bound to hydrogen. Nitrogen is much more electronegative than hydrogen, and so we'll see electron density being pulled away from the hydrogens towards the nitrogen. And so here we see that there's a net dipole in this molecule, primarily focused upon making this central nitrogen partially negative. These are all partially positive. We see that this is a polar molecule. So if it's polar, we can either say that it's going to be dipole-dipole or hydrogen bonding, and that is determined by whether or not there is an HFON bond. We see here that we have two nitrogen-hydrogen bonds, and so there is an HFON bond. The strongest intermolecular force is H bonding. Moving on to SF4, I'm going to draw it with Vesper just to imply more of the geometry. This shape is seesaw. So this seesaw shape lends itself well to electron density being pulled away from the sulfur towards all the fluorines. So there is a net dipole in this molecule that leaves the sulfur partially positive and all of the fluorines partially negative. So we see that it's a polar molecule. It's either got dipole-dipole interactions or H bonding, and we have to determine which one. Does it have any HFON bonds? There are no hydrogens in this molecule, so we can say no to that. And so the answer here is just dipole-dipole interactions. We're looking at KRCl2 next. To draw this out with its geometry in mind, giving it an overall linear shape. We see electron density being pulled away from the krypton in two equal but opposite directions, meaning that they cancel out and there's no overall net dipole moment. So that makes this a nonpolar molecule. And the only intermolecular force that act upon nonpolar molecules are London dispersion forces. Now looking at CH4, or methane, we know that methane is a tetrahedral compound. The electron density is being pulled slightly in towards the carbon since it's a little more electronegative than hydrogen, but it's being pulled equally from all the same directions, and we can say that this is a nonpolar molecule. As previously mentioned, nonpolar molecules can only have one intermolecular force, and that is London dispersion forces. Last but not least, we have carbon monoxide, or CO. To draw the Lewis structure of that, looks kind of like this. To include the formal charge on here, we have a positive charge in the oxygen and a negatively formally charged carbon. So in terms of electronegativity, we know that oxygen is more electronegative than carbon. So we'll actually have a partially negative charge on this oxygen in terms of electronegativity and a partially positive charge on this carbon. This is a polar molecule. So we're going to ask ourselves that same question of, does it have dipole-dipole interactions, or does it have H bonding? Does it have any H bond bonds? There are no hydrogens, so there are no H bond bonds, and therefore the strongest intermolecular force we see here is dipole-dipole interactions.